But on Flight 447, the fault message suggests major pitot problems.
The airspeed indication systems, all three of them, were compromised.
In the wind tunnel, Tony Cable tries to find out why.
Okay, Cliff, can you take it up to 30 knots for a try this time?
A sensor inside the pitot tube measures the pressure of the air rushing into its open end. The computer converts the pressure into airspeed, in this case, around 30 knots. But Cable can trigger a malfunction just by blocking the tube. The measured airspeed drops to zero. But what can block a pitot tube at 35,000 feet?
The pitot tube sticking out into the airstream means it's vulnerable to being hit by ice and rain. It's a small device, small things pick up ice quicker than big things, so the pitot tube is prime candidate for picking up icing.
To combat ice, the pitot tubes are designed with powerful heaters, intended to handle any conditions, including full-blown storms. So what caused them to fail? The answer could lie within the storm itself.
One of the things that we're interested in is what were the conditions at 35,000 feet? What kind of ice or liquid was there at that altitude?
John Williams turns again to the new NASA satellite images.
One of the first things we want to do is try to figure out what the temperatures were at that level.
He creates a cross-section showing the temperature at different altitudes.
What it shows, starting at the surface and going up to the top of the atmosphere, they were flying at this level here, and you can see that the temperatures were about 40 below at the time and location of the accident.
Minus 40 may seem extremely cold, but in fact it's much warmer than is usual at 35,000 feet. These temperature readings suggest that an unusual phenomenon may have occurred.
What we found out from this analysis is that it's possible that there was supercooled liquid water at the altitude of the aircraft.
Supercooled water is a weird quirk of physics, where extremely pure water remains liquid at temperatures well below freezing. In 32 years' experience, Tony Cable has never actually seen this phenomenon up close. The purified water in these bottles is well below its normal freezing point, but it's still liquid. Ice crystals can only grow around tiny particles, like impurities or bubbles. When Cable inserts a metal tube, instant ice.
That is incredible.
The fact that air is really clean over the oceans suggests that if there's supercooled liquid water in the atmosphere and an aircraft flies through that, those little droplets are ready to freeze as soon as they hit a surface.
Supercooled liquid water could overwhelm heating elements in the pitot tubes and freeze them in seconds.
It is possible that the aircraft encountered conditions which are more severe than those to which it had been designed. The pitot heads may not have been sufficient to cope with these severe conditions.
The team discovers that pitot tube failure is not uncommon. In the 6 years leading up to the loss of Flight 447, the French authorities identified 32 failed pitot events involving A330s or similar A340s. And in 2009, the number of incidents is alarming.
It was in the order of 1 a week for getting on for 2 months in the period leading up to the 1st of June.
Just 6 days before the crash, 2 pitot tubes fail on a similar A330 flight from Rio to Paris. The pilots managed to keep control of the aircraft. All the failing pitot tubes meet existing safety standards. Still, in late 2007, Airbus recommends that all A330s receive improved pitots. Air France is in the process of upgrading its entire fleet when Flight 447 runs into the Atlantic storm. When the aircraft's pitot tubes fail, the automatic systems shut down, forcing the crew to take manual control.
When things go very wrong, the last line of defense is the aviator.
After more than 3 hours on autopilot, the crew suddenly face information overload.
That crew faced an almost unheard of series of failures, one right behind the other. And for them to sort through it would have been very difficult that night. Why is the airplane doing what it's doing? What are all these failures? Why are they all coming at one time?
Bombarded by faults, the crew must cope with the most serious problem of all: maintaining a safe airspeed. At high cruising altitudes, the speed range that all commercial aircraft fly inside gets very narrow.
Our speed range is quite limited. Typically it could be 10 knots either side of the cruise speed.
If Flight 447 speeds up or slows down by as little as 10 knots, it could suffer a potentially lethal condition known as a stall. Tony Cable demonstrates what happens.
Okay, Cliff, you ready to go?
An aircraft gets its lift from smooth, streamlined airflow over the wings. If the aircraft slows, the angle of the wing must be increased to maintain lift. But too slow, and there's an angle where the airflow breaks up.
If you disrupt that flow, the wing cannot produce lift. And that's really all a stall is it's a disruption of the airflow across the top of the wing.
If it slows down, there's a tendency for the nose to come up, and at a fairly shallow angle, the wings will stall, the airflow breaks down, there's a loss of lift, and the aircraft begins to descend.
But if too slow is a problem, so is too fast. If they don't know their airspeed, a pilot can overcompensate by speeding up. As an ordinary commercial airliner gets too fast, a shockwave develops on the wings. This can also disrupt airflow, triggering a stall. In either scenario, stalled wings could mean a dramatic, uncontrolled descent. The pilots must avoid slowing down or speeding up by as little as 10 knots. But with their pitot probes frozen, they have no way of knowing their precise airspeed.
The ability for the crew to recognize if they were at the proper speed is going to be a much more complex problem now.
But can this complex problem be solved? In the simulator, Martin Alder recreates the known technical failures on Flight 447.
Let me know when
He wants to know if two experienced pilot instructors can maintain speed and avoid a stall using standard operating procedure. The pilots don't know what they are about to face.
Could you give Brest a call, see if there are any ride reports of Flight 355?
Like Flight 447, they are cruising at 35,000 feet at night over the ocean. Alder unleashes a storm.
I like the look of that one, so now activating.
Thunder clouds loom ahead on the radar.
Probably in line of thunderstorms, about 10 miles away.
The captain plans a detour and prepares for turbulence.
So turbulence airspeed, then I'm selecting decimal 76.
As is likely on Flight 447, the pilot selects a slightly lower speed to reduce stress on the aircraft. Auto thrust automatically reduces engine power.
Hi, ladies and gentlemen, the captain speaking. We are just approaching an area where there are a few rain showers around. We've put the seatbelt sign on for approximately 10 minutes or so.
As they edge around the storm, Alder triggers the critical moment of Flight 447. He fails all three airspeed indicators.
Okay, we have a nav ADR1 fault. We have unreliable airspeed.
The automatic flight control systems shut down.
We're flying with no autopilot or port thrust.
Okay, autopilot's on. I have control.
You have control.
If their actual airspeed rises or falls by as little as 10 knots, they could suffer a catastrophic loss of control. But the pilot uses standard procedures learned in training. He moves the throttle levers to set thrust at exactly 85%.
And I'm selecting, I've got 85% set.
Then he raises the elevators to pitch the nose up at precisely 5 degrees. With engines at 85% power and 5 degrees upward pitch, the aircraft should always settle at the same safe speed.
It's quite possible to fly the aircraft to actually quite high standards of accuracy. Something in the region of about 5 knots or so of the desired target speed would be quite achievable for most crews.
To get radar contact with the next
Without airspeed indicators, pitch and power is a pilot's lifeline. These pilots ignore any fault messages until they are safely in control.
Got 5 degrees on the standby, 4 degrees on the other.
Flying the aeroplane is the prime objective. No matter how attractive the messages might be to anything on the flight deck, you both concentrate on ensuring that the person who should be flying the aeroplane is flying it and flying it in the manner which is safe.
Okay, so we've got what I think is basic control of the attitude. We're bumping a little bit with the weather, but generally that's safe.
With no reliable airspeed indicators, maintaining pitch and power can get them to the nearest airport. The emergency is over.
That's it. It's finished.